Sercel, whom I met 30 years ago at JPL.
Yeah,
Something like that.
Yes.
I think we got the whiskers to go
When I
with
was
that,
in grad
that analogy. And Joel is the odd individual who combines
You can just stop it at odd
technical expertise and business acumen. So Joel, talking about small bodies.
Thank you so much, John. As I like to remind him, when we met, I had hair. I'm going to talk about asteroid mining and the technology that we've been developing for the past few years under sponsorship from a couple of different sources. One, very grateful, the NIAC program within NASA. The other from our private sector investors, who include some folks from Silicon Valley and some folks from Europe. I'll just mention that I'm the founder and president of TransAstra Corporation. I'm also the CTO of Momenta Space, which is a water-based space transportation company funded in Silicon Valley. It just went through Y Combinator, and we just closed a significant investment round. It's water-based plasma propulsion. And the two companies are strategic partners, so they support each other. I want to emphasize that the work I'll be talking about here is work of a collaboration of really the top people in several different fields. Probably the top guy in what I'll call asteroid and meteorite geology is Professor Dan Britt from the class group at University of Central Florida. He's got a fantastic postdoc by the name of Kevin Cannon. Chris Dreyer is an associate professor at the Colorado School of Mines, where we're building our optical mining test bed, which I'll talk just briefly about today. Jim French is the co-author with Michael Griffin of the book on space vehicles and launch vehicles. He's also been a key technical advisor at Blue Origin for some guy named Jeff since I introduced them 15 years ago. Anthony Longman is a NIAC fellow in his own right, and he's an architect and the artist who's now become a spacecraft configuration engineer, because innovative people learn new skills. Stan Love is an astronaut who used to be a student of mine at Caltech. I taught spacecraft and mission design for a dozen years at Caltech and ran a systems engineering lab there. And Stan is an expert on asteroid physics, but he's also our advisor on space mission operations, having done 16 hours worth of EVAs. And he was actually the first astronaut to work in the new paradigm that Franklin was talking about this morning, which is instead of training for a specific space, EVA, he learned general EVA tools, skills, and saved the space station. And that was not by plan. It was because the guy who was supposed to do the EVA got sick, so he just went out and did it. So why am I working in this area? So I just saw Jason smiled. He smiles when I show this chart sometimes. In 2014, I was pretty much out of the space business. And the NASA Advisory Council wrote a report that had a hard-hitting sentence in it. It said, the mismatch between NASA's aspirations for human spaceflight and its budget is the most serious problem facing the agency. The political class has made it really clear to NASA, you get of rough order $20 billion a year. To some people, that doesn't sound like a lot of money. To others, it sounds like a lot of money. But you got to figure out how to do something exciting within that budget. And what the Advisory Council told NASA is, you have all these exciting missions, but you can't afford them to do within that budget. So the question is, what does asteroid mining have to do with that? And I'm going to answer that question. The answer is, as was made reference, John Mencken said it eloquently this morning. Back in the Apollo program, we came back from the moon and we thought it was arid. We thought space was arid. And one thing that we've learned in 60 years of space exploration is everywhere we go, there's volatile materials and water. And water is really important for humanity. About 1 in 4 near-Earth asteroids is a carbonaceous asteroid, and they contain water. It's not molecular water, it's not water ice. It's water of hydration, which is molecularly bound to the minerals, and also they also contain carbonates, which is essentially a source of CO2. If you take a little sample of a carbonaceous asteroid, put it in the bottom of a test tube, put a cork on the test tube, heat it violently over a Bunsen burner, the expanding steam will blow the cork off. If you heat it gently, the expanding steam will condense on the inside of that test tube because there's water in them there hills. And that water is the primary ingredient in rocket propellant, radiation shielding, drinkable water for human beings, and for many other applications in space. It becomes very important for humanity's future in space. Now, a lot of people think that the moon is the closest object to the Earth in space. So that's actually false on a couple of different levels. One is we know mathematically that right now, between the Earth and the moon, statistically there are on average a dozen asteroids that are gravitationally bound to the Earth-Moon system. They're called mini-moons, and they come in, they get gravitationally bound for a year or two, and then they're ejected. About once a week, a 10-meter class asteroid flies between the Earth and the moon. 10-meter class asteroid is 1,000 metric tons. If it's water-rich, and about 1 in 4 of them are, each one of those contains about 100 metric tons of water, and maybe 7 or 8 metric tons of other volatile materials like carbon dioxide, carbon monoxide, and methane, also very useful materials in space. But more important than distance is delta V. And the statistical models that we have of the asteroids show that there are thousands of asteroids at delta V's that are significantly less to return resources from those asteroids than to get resources from, say, the surface of the moon. And this business of prospecting the asteroids using statistical modeling and telescope technology has been a big part of what TransAstra has been doing with the help of our NASA and private sector sponsors. This particular plot happens to be something that was published in the journal Nature by the planetary scientist Rick Binzel from MIT. I think it was in the fall of 2014. Now, there's a lot of asteroids. There are billions of asteroids. Asteroids are spread throughout the solar system, and everyone always thinks of the asteroids as being the main belt asteroids between the orbit of Mars and Jupiter. But in fact, the more interesting ones for economic considerations are the near-Earth objects that are closer to the Earth. An object is said to be a NEO if it passes within 1.3 AU of the Sun. The statistics on NEO, this is actually from one of my co-authors from his publication in Nature. There's a team, Jedicke, Botke, and Gronvik, who maintain the most definitive statistical model of the distribution of asteroids in the NEO belt. Botke was one of my students at Caltech back in the day, and Jedicke is my collaborator from the University of Hawaii Institute for Astronomy. This is from their more recent Nature publication. And what this shows is the statistical model, and we have really good reasons for believing this statistical model, for the total number of NEOs. And within the error bars, there are about 300 million NEOs of 10 meters in diameter or larger. The problem is we know where all the big ones are, but we don't know where the little ones are because the telescope technology hasn't been applied in a clever enough way. And it turns out one of the things that we've been working on is a breakthrough in telescope technology to find all these. And in doing that, we've modeled the distribution of the resources in the NEO belt. How much water is there in what size objects distributed over what orbits and what delta V's. What we show is there on the order of 1,000 mineable asteroids with masses on the order of 1,000 ton each containing about 100 tons of water. That's enough to run any space industry that you can imagine for decades. These are only the extreme low delta V targets. If we go out well into the NEO belt, we're talking about hundreds of millions of targets. Just to give you an example, one of the more recently discovered asteroids is this one 2018 PK21. And the delta V to return resources from that asteroid is 670 meters per second. Recently redid this calculation for Ryugu, the asteroid that the Japanese have their spacecraft at right now, and it's less than 2 kilometers per second from that. That asteroid is covered with about 1,500 500-ton boulders. Just to put that in context. The magnitude of this resource is extreme. By the way, watch for the new science fiction book Delta V by the best-selling author Daniel Suarez. It'll be coming out in a little bit. I was just reading the galley proofs, and the technology I'll talk to you about today is featured prominently in that book. Hang on, my timer went off. I want to see where I am in time. Oh, I'm fine. So, in 2006, the Director for National Intelligence asked me to look for what are the disruptive technologies that are going to change. I used to be a management consultant. I spent 14 years at JPL. That's when I knew John. And he started the NSTAR project, which was the ion propulsion system that's on the spacecraft Dawn, which recently had the end of its mission. It had visited the asteroid Vesta in Ceres. I wrote the first version of that proposal when I was at JPL, doing my PhD at Caltech, and running the Advanced Propulsion Concepts program then. But things were going kind of slow for me in the space business, and I wanted to go do faster. I mean, we started NSTAR in 1992, and the NSTAR propulsion system just turned off. It was just a little too slow. So in 99, I left JPL to go and teach at Caltech, taught satellite design, astrodynamics, ran a systems engineering lab, and kind of got out of the space business. Did a few things in space, helped Jeff Bezos set up Blue Origin, did studies for the national intelligence, that sort of thing. And one of the things that just kept niggling at me was the space was about to get exciting, but the question is, when was it going to get exciting? So I spent time with Elon in around 2006, and then around 2013, another branch of the government asked me to do due diligence on SpaceX because they were thinking about buying SpaceX rockets. I came out of that, and it was like an acid trip. It seemed very clear to me at that point that SpaceX was going to be successful, and we were going to have order of magnitude reductions in the cost of getting into space. Not with exotic maglev things, but just good engineering. And I thought this is the time to get back into space. And I asked myself, well, what's the right thing to do in space? So my first ever consulting contract when I was a young engineer was from a guy named Gerard O'Neill at the Space Studies Institute. And I'd been looking at building big things in space and what the resources of the solar system were. And back in the 1970s, we thought there was enough material in the asteroid belt. Actually, Gerard O'Neill did this calculation, that if you put everyone behind 5 meters of shielding and build Earth-like worlds in space, how much material is there in the asteroid belt and what kind of a population of humans could you support? And his conclusion was you could support a population of 3 trillion people with a land area 1,000 times that of the Earth. That's why we're interested in asteroids. It's for an unlimited future for our children and their children as far as the eye can see. So asteroids have always been a fascination to me. And so I happened to go on vacation. While I was on vacation, I read John Lewis's book on asteroid mining. I thought, well, geez, that's a good business to get into. So I started to think about, well, let's turn these concepts that a really great scientist came up with into engineering reality, because that's what I like to do. And in his book, John Lewis suggested that we can put asteroids in bags and bake them. So I wrote a proposal to NASA, to the STMD ESI program, to test that theory. So this is the chart that was in the proposal. It proposed to put an electric oven in a big vacuum tank and put meteorites and asteroid simulants in the oven. We did that work. And we have used that to bake more asteroid material than anyone else in the world. and cryotrap it and show what comes out. We collected water, carbon dioxide, carbon monoxide, and methane. The problem is, what we found is that baking is not a practical solution because the thermal time constants are too long. The thermal time constant of a 10-meter, 1,000-ton asteroid with all the thermal fractures and everything that you can expect in the regolith layers and so on is measured in at least decades and maybe centuries. So if you want to wait 100 years to get all your material out of the asteroid, feel free to bake. But in the business of business, you got to go fast. So we stumbled across a very interesting piece of physics. And what that physics says is that when you concentrate sunlight onto the surface of a rock, it causes thermal stress in the rock and it fractures. And then that fracture breaks off a little piece of the rock material. And those little chunks, if you're going after a water-rich target, have a low thermal time constant, so they very quickly outgas. When they do, they clean the surface, and then that gas can be collected by cryotrapping. And then what happens is the surface, which has now been cleaned, is cold again, so the beam of sunlight continues to spall the surface. Now, you could make the radiation more intense and ablate the surface, but there's reasons why you don't want to do that. Spalling, it turns out, is the way to go. You can vaporize the surface. You also don't want to do that. Spalling is the most efficient. If we had a few hours, we could talk about why. We did dozens of experiments.
This slow-motion clip shows a plume of water being ejected from a small sample of hydrated rock before the rock disintegrates due to the rapid release of water vapor. In this clip, we excavate a hole while extracting water and CO2 from a sample of asteroid Simulant, which was prepared for this purpose by the University of Central Florida for our test program. Finally, this video shows an unexpected re-entrant fountain of asteroid Simulant, which was produced in a vacuum chamber as we were exploring the use of optical mining techniques to mine regolith, such as that which might be expected on the surface of a water-rich asteroid.
So what we showed, in essence, is that by using concentrated sunlight, in some of the experiments we use simulated sunlight, and some we use actual sunlight, that you can dig holes in asteroids 100 times faster than you can by baking them. So then the question is, how do you make practical use of that? Well, people had talked about bagging asteroids for decades, and it turns out that JPL, as part of their ARM mission proposal, under their Option A scheme, had spent millions of dollars and published the result of reducing the process of bagging an asteroid to practice. This includes the design of the bag, the design of the control systems, and if we had time, I could show you animations of our own designs of this. But it's at TRL 4. It's eminently feasible from an engineering perspective. You just need to do the work on it. So you can bag an asteroid. And what we did was we designed an optical system, which I'll detail more in some following charts, whereby we introduce highly concentrated sunlight onto a spot on the asteroid and use it to chew up the asteroid. Okay? As we're chewing up the asteroid, excavating the asteroid, we're collecting the debris that comes out and bagging it to use as radiation shielding. And we're taking the gas that's removed through this process. It fills the primary bag at a pressure of about 10 to the minus 3 atmospheres, about 1 torr. So that's a vacuum by terrestrial standards, but in space it's enough to maintain the engineering rigidity of that bag. We have a big hole in the side of the bag, and through that hole we have a secondary bag, and that secondary bag is passively cooled by thin film secondary surface mirror, and it's cryogenically cold, and the volatile material is cryopumped into that second bag. By the way, we've done more practical work in cryopumping at ISRU experiments, I think, than anyone else in the world. We have liters of liquid or frozen volatiles that we've extracted in our experiments and cryopumped. And so our models, so I developed a mathematical model of this process, including the heat transfer and gas dynamics. Let me just see how we are on time. We're good. And showed that for a 15-meter class asteroid, for a system that would be launched on a Falcon 9, In 3 months, we could extract 100 tons of ice. So
Optical mining of asteroids can be a technological breakthrough that turns thousands of asteroids into refueling stations for spacecraft.
But first, Joel Sercel has to see if he can actually extract vapors from an asteroid.
So we've done subscale.
In other words, he's trying to get
and this
water
is a
from
full-scale
a stone.
demonstration.
Here we are at the White Sands Missile Range at their solar furnace facility. What we're going to be doing is sunlight from the sun is going to bounce off that giant mirror back there, and it sends the rays through this giant Venetian blind, and it'll go into a parabolic reflector and focus it down into a little 4-inch circle. Now we will have asteroid simulants inside of a vacuum chamber. The sunlight will hit the simulant, and when it does, it'll be so intense that it'll fracture, break the surface of the simulant, and drive vapors out of it, water and carbon dioxide. And as those vapors are driven out, it'll excavate or dig holes in the asteroid's area.
3, 2, 1, open.
There you see the spalling process. And it works just as the math model predicted.
Okay, let's shut it down. You can tell exactly where the light was coming in. It's right there. So what happens is, as a highly concentrated light comes in, it breaks the surface of the material, and it heats the material. When it heats up, it lets out water vapor and carbon dioxide. The process of breaking the surface and digging holes is called spalling. As you can see, we dug a big hole. And the spall process released debris, which is all collected inside the tank.
The dream of asteroid mining is alive and well.
We think that this could be a very important transition for mankind as we move from being a purely terrestrial species to being a spacefaring species where our industries go in space. At that point, it will be possible for people to actually go and colonize and settle space.
So in our experiments, we validated our mathematical model of the process. Now, in mining, you don't get within 0.6 of a degree Kelvin. We were within a factor of 3, which is considered really good if you're working with natural materials like this. And we're continuing to do this work under our Phase 2 NIAC funding, and we are very appreciative of the NASA program. This is really, if you look at the history of the United States, public-private partnership has been one of the things that's really helped the country massively. And the classic example is the Transcontinental Railroad, which was a public-private partnership between private investors and the federal government that paid for itself hundreds and hundreds of times over and made the United States an economic superpower. Right now we have a situation where the investment community is looking very hard at space and investing heavily. The wealthiest human being in the history of the planet has said that it's more important than his day job, which is running Amazon, and he puts in a little more than $1 billion a year. And we're about to make this happen as a community in partnership with NASA and the investment community. Now, I'm a big believer in nuclear power in space. In fact, I think that if God meant humanity to use nuclear power in space, he would have put a giant nuclear fusion reactor at the center of the solar system. While using solar power on the Earth has problems because of atmosphere and weather and that sort of thing, and you saw that big solar reflector I showed, it's like it has to be built like a bridge to last on the ground. This is a 14-meter diameter reflector, which if used as a concentrator in space would have about the same performance of that one that I used at White Sands in the demonstration I showed you. The difference is this lenticular structure could be folded up and put in a carry-on bag and carried on an airplane. And at that power, it gives you about 150 kilowatts of very low cost, very high performance power, which you can focus onto a heat exchanger and get essentially identical performance to a nuclear engine for deep space missions. It doesn't give you the thrust for breaking out of low Earth orbit, but for a minor penalty in performance, you get a huge reduction in cost. These things are very lightweight. the technology has been at sort of TRL 6 for decades, and it's time to turn it into TRL 9 and start using it for practical applications in space. This happens to be a paper on solar thermal propulsion that I wrote, I think it was 1987, again, back when I had hair. The specific impulse of a hydrogen solar thermal engine is just about the same as a nuclear solar thermal. With water, if you go to thorium oxide as a heat exchanger material, you can achieve a specific impulse of about 400 seconds, which is actually ideal for asteroid mining if you're going after the low delta V targets. And so we've designed something we call the Omnivore Thruster, which is a solar thermal engine that can use any volatile material as propellant. And we intend to test that in our laboratory that I'll tell you about in a minute, along with our optical mining experiments. As I said, NASA invested millions in asteroid bag capture technology. This is a OV1 type view of an asteroid mining mission. A single spacecraft, roughly the mass of a Ford F-150, flies out to an asteroid roughly the size of a single-family home in New England and captures 100 tons of ice from it. And over the life of that spacecraft, it can do it 3 times. So think in terms of, a few thousand kilograms launched into space can return 300 tons of propellant to the cislunar system over the life of the mission. We've designed a complete architecture of space transportation based on asteroid-derived propellants, and we're working with others on how to use asteroid regolith for radiation shielding for human habitation. Eventually, the key to humanity's future in space is the resources of the asteroids to build worlds for humans to live in terrestrial-like environments. We've designed a series of space missions based on this architecture. And also, it seems quite likely that the Martian moons are volatile rich. That's not known yet, but it seems very likely. Every time planetary scientists say, when we go to that body, we're not going to find volatiles, they've been wrong. We even know for sure that Mercury's poles contain large quantities of frozen water ice. Mercury. So there'll be water where we go, and this architecture can dramatically reduce the cost of human exploration of Mars also. So we did a cost analysis. NASA Ames, through the Space Portal, this was originally funded out of the NASA Chief Technologist Office, Alexander McDonald. When we looked, if NASA were to do an aggressive and exciting program of human exploration over a period of 20 years, how much would it cost? The actual number came out, let's just say, very high. So what we say is 400 billion, but that's based on really tweaking the cost models. If you look at actual recent NASA costs from SLS and Orion, it's much higher than that. This would be the most efficient human space programs NASA has ever done. And if you work that out compared to the budgets that Congress has given NASA, it's a non-starter. Congress is really clear on that. But we think the key to humanity's future in space, and NASA playing an absolutely pivotal role, is 2 things. Space resources, especially asteroids, and public-private partnership. If you move just from traditional NASA contracting to commercial business practices, but you're still supplying from the Earth, you save about $100 billion. So commercial business practices are a real help. If you use traditional contracting, but you get all your propellant from the asteroids, you save about $250 billion. You start to get into the realm of affordability. But when you go to public-private partnership and asteroid resources to eliminate the need to launch materials from the Earth, the total cost over 20 years goes down under $100 billion. That fits within the NASA budget, and you could do every one of the exciting missions that NASA is wanting to do. What's our next step? This is a picture from inside of our laboratory. That is the biggest light bulb in the world. The right way to do sunlight on the Earth is to simulate it. So we have a 32 kilowatt light bulb that draws 700 amps at 45 volts. It's the equivalent of 3 massive IMAX projectors. And we'll have the ability to put that into a circle this big. We've had a few setbacks with burned out circuits and that sort of thing, but we should be turning it on this week. That's the core of our optical mining test bed. The optical mining test bed uses a vacuum tank that's about this tall and about 8 feet long. And we're making simulants of asteroid material. We've already validated the simulants in past research programs. And we've designed the Honeybee spacecraft to be launched on a Falcon 9 and the Queen Bee to be launched on a BFR. A single Queen Bee can fly out to a 40-meter class asteroid, and instead of taking 3 months to mine it, it takes a full year. It brings back 3,000 tons of propellant in a single mission. That's enough to run the entire space program for a decade in space. We've also designed this little guy we call the Mini Bee. It's got all the features of the Queen Bee and the Honey Bee, but it's designed to be launched either on an Espa Grande or one of these little launch vehicles. This artwork shows it on a Virgin Galactic Launcher 1. And the idea is that we would launch it with a synthetic asteroid that we would make, toss them both out into low Earth orbit, and capture that little miniature asteroid, mine the water out of it, and use that water to demonstrate solar thermal propulsion in space. At this point, we will have reduced every one of the technologies in the APIS architecture to practice in space. And we have a detailed roadmap of all the things we need to do. We have a bunch of small steps that need to be done on the ground and some big steps that need to be done in space. The small steps that need to be done on the ground are more rigorous mission designs, more rigorous. So we've published in the refereed journals our models of the population of asteroids. We need to do the next level of detail. We have a proprietary telescope prospecting system that I wish I had time and could tell you all about today, but we're confident that we can find all the asteroids. The optical mining test bed is built. We'll be using it to mature the TRL of the actual optical mining process from 3 to 4 in the next few months. We'll be using the light source in the optical mining test bed for the first long-duration, high-performance solar thermal rocket propulsion. We're going to be building an engineering model Mini-Bee with a thin-film reflector, and we're actually going to demonstrate the optical performance of that reflector on the ground. More detailed modeling of the optical mining process. And also, we've got to get into the robotics a little bit more than we have so far. So that's the near-term roadmap for things that we want to do on the ground. The larger roadmap includes some flight experiments on the space station, flying Mini-Bee. The telescope survey that we've designed is called the Sutter survey. And we think that within 10 years we can launch the first Honeybee mission to go out and get 100 tons of ice and kickstart the cislunar economy and transition to Queen Bee, and we've designed something called Sutter Ultra that will find basically every asteroid in the Neo belt. So we see 10 years to full-scale asteroid mining. And just philosophically, I just want to comment before I get off the stage here. I've got, how many more minutes do I have? Okay. The thing that's making this happen is that there are historical figures that are making it happen. Jeff Bezos, Elon Musk, people like that. Practical engineering is making it highly cost-effective for businesses to move in space. Bezos has pointed out that college kids can start internet unicorn companies from their dorm rooms, but they can't start space companies from their dorm rooms. He's building the infrastructure to make it so that entrepreneurs can start unicorn companies from their garage. This is going to completely revolutionize space. And it starts with low-cost launch, and now I'm out of time. And the next step beyond that is harnessing the resources of the solar system. So thank you very much.